Greetings, everyone. This is Professor Roman. Let's continue the group theory lectures. We just completed our overall discussion of cyclic groups, and I want now to talk about the Euclidean group. As we have briefly discussed back in Chapter 2, as was example 2.11, a rigid motion of the Euclidean plane R2, which is also called a Euclidean motion or an isometry, is a map, sigma, from the plane to itself that preserves distance. And since the distance function, it's a metric, is positive definite, an isometry is injective. And later on we'll show that isometries are surjective, and so they are bijections. Now we denote the family of all isometries on R2 by E sub 2. Since the composition of two isometries is an isometry, composition is a binary operation on E2, and since the identity map is an isometry, and so is the inverse of any isometry, E2 is actually a group under composition, and it's called the Euclidean group, which is why it's denoted by E2. This group has two very important subgroups. First, the family of all translations of the plane is a subgroup of E2 called the translation group, and I'll denote that by T sub 2. Specifically, a translation by an element A in R2 is an isometry. I'll denote it by tau sub A, and tau sub A of x is x plus A. So it's just addition by A. The other important subgroup of the Euclidean group is the family O2 of all isometries that fix the origin. So they send the origin to itself. This is a subgroup of E2 called the Orthogonal Group. And since the only translation that belongs to the orthogonal group, in other words, the only translation that fixes the origin is the identity map, these two subgroups are essentially disjoint. Now we can characterize isometries as follows. First, translations, rotations about the origin, and reflections about a line through the origin are all isometries of the plane. And in fact, all isometries of the plane are one of two types: a rotation about the origin followed by a translation, or a reflection about a line through the origin followed by translation. In case I forget to say about the origin, from now on rotation means rotation about the origin, and reflection means reflection through about a line through the origin. So to see why isometries are one of two types, these two types, let's make some simple observations. First, a triangle formed by the origin and any two distinct points on the unit circle is a right triangle if and only if the distance between those 2 points on the circle is the square root of 2. This follows from the Pythagorean formula. Second, an isometry sigma is completely determined by its values on the 3 points, the origin, this is the point 1, 0 on the positive x-axis, this is the point 0, 1 on the positive y-axis. And the reason that's the case is because we have these three equations. The distance from sigma x to sigma 0 is the same as the distance from x to 0 Distance sigma x sigma p is the same as distance x p, and so on. So the distances here on the left side of these equations are known for all x in R2, because we know the right sides. Obviously, if we know x, we know its distance from those 3 points, 0, p, and q. So we know the distances on the left side here. But a little elementary geometry will show that these 3 distances determine the value of sigma x. And since this happens for all x, the map sigma is completely determined. And I'll tell you a secret, since I got a B in high school geometry, I'll let you do the geometry here that's required. Okay. Also, by the way, since a member of the orthogonal group fixes the origin, it is completely determined by its action on P and Q. And that will prove to be quite useful. Third, a translation tau of the plane is completely determined by what it does to the origin. So specifically, if tau is a translation and tau of 0 is A, then tau has to be translation by A. Fourth, if sigma is an isometry and sigma of 0 is A, then this isometry, tau negative A sigma, the composition here, fixes the origin. And so it belongs to the orthogonal group. So here it is in symbols. And so what this tells us is that an understanding of the orthogonal group, its members, is the key to understanding the full Euclidean group, because all we have to do is apply a translation after we apply a member of the orthogonal group. So, now consider the right triangle with vertices 0, p, and q. And I have a figure here. I'd like to have both things going on at the same time. I think that will do it. Okay. If sigma is a member of the orthogonal group, then sigma p and sigma q also lie on the unit circle, because their distance from the origin is 1. And since the distance from sigma p to sigma q is the same as the distance from p to q, which is the square root of 2, it's this line here, the hypotenuse of this right triangle. The triangle origin sigma p, sigma q is also a right triangle. And so these two triangles are actually congruent. The two right triangles, OPQ and O sigma p sigma q. So, if we rotate this triangle OPQ counterclockwise about the origin through the appropriate angle, which I've marked as theta, so that the two triangles overlap, then one of two possibilities will occur. One possibility is that P will be sent to sigma P and Q to sigma Q. This triangle is rotated so it overlaps the dark triangle. The vertices will be coincident. So P could go to sigma P, Q to sigma Q. But the other possibility is that P could go to sigma Q and Q to sigma P. The difference here is a difference in orientation of the dark triangle. Now, we know that sigma being in the orthogonal group is completely determined by its effect on the 2 points P and Q. So what does this case tell us about sigma? It does the same thing as the rotation through the angle theta, because that rotation sends P to sigma P. So the rotation has the same effect as applying sigma, to both P and Q, therefore it is rotation. So sigma is rotation through this angle theta. And I'll use this notation for the counterclockwise rotation about the origin through the angle theta. In this case, the relationship between sigma and rotation is a little more complicated. Sigma has the same effect on P and Q as first doing the rotation through angle theta, so the triangles are coincident, but the vertices are mismatched. The rotation sends P to sigma Q, not sigma P. To fix that, we have to follow the rotation by a reflection. It's about this dotted line that will swap sigma P and sigma Q. So then P will get sent to sigma P. So that is reflection about the line through the origin that makes the angle theta plus pi over 4 with the positive x-axis. So then sigma is the composition of rotation followed by this reflection. But I'm also going to leave it as an exercise to show that the two operations here can be performed by a single reflection, and it's this reflection. I'll give you a tiny hint. So if you don't want the hint, then mute the video. Rotation or reflection can be represented by matrices, matrix multiplication, and so that'll make this easier. If you have a real geometric bent, you can probably figure this out without using matrix algebra, so we'll leave that for you. But the upshot is that every member of the orthogonal group is either a rotation, this one here, or a reflection. So now if sigma is a member of the Euclidean group and sigma sends 0 to x, we've already seen that this composition is in the orthogonal group, so it's either a rotation or a reflection. And so sigma is either a rotation followed by a translation or reflection followed by translation. And because these two subgroups, the translation subgroup, the orthogonal subgroup, are essentially disjoint, and what we have just said here amounts to saying that E2, the Euclidean group, is the essentially disjoint set product. Translation group, orthogonal group. So if we know everything about the orthogonal group, the translation group's very simple, we know the Euclidean group. As a final point, the members of the orthogonal group are linear maps because they're multiplication by an appropriate 2x2 real matrix. But the translations are not linear except for the trivial translation, in other words, the map that does nothing, the identity. Perhaps the most famous family of groups inspired by geometry is the family of dihedral groups, and we've touched upon them, or at least a few special cases of that family already. The dihedral group of the square D8 and the dihedral group of the hexagon D12. these groups are subgroups of the Euclidean group. So if P is a non-empty subset of the plane, then a symmetry of P is an isometry of the plane that sends P onto itself. So for example, rotation about a point, I probably shouldn't call it P, I should maybe call it Q, is an isometry of any circle centered at Q. Okay. So P is the circle that we're creating the symmetry for. If n is bigger than or equal to 3, then let's let P be the regular n-gon in the plane, centered at the origin, one of whose vertices lies the positive y-axis. So this would be the case n equals 4, n equals 5. We will also label the vertices. The vertex on the positive y-axis is labeled 1, and the other vertices are labeled consecutively in a clockwise manner. This is customary. The symmetry group, which I'll call Gn of P, consists of all the symmetries of P. And it's possible to show that the symmetries of the polygon are the same as the symmetries of its vertex set, V. So it's customary to regard this symmetry group Gn as the symmetries of the vertex set. In fact, a symmetry of the vertex set is just a permutation of that vertex set. And so it's also customary to think of the elements of the symmetry group of a polygon as permutations of the labeling set 1 through n. Or in other words, as elements of Sn, the symmetric group on n symbols. But it's important to note that not all permutations of V are symmetries of V, because symmetries have to preserve adjacency, permutations of V do not. Our plan is to prove that each symmetry of V does preserve adjacency, and so it can be expressed as a composition of certain rotations and reflection across the vertical axis. This one-click clockwise rotation of P is given by the n cycle, 1, 2, up to n, because it sends 1 to 2, 2 to 3, and wraps n back around to 1. So that's just turning the dial, a one-click rotation clockwise of the polygon. Reflection across the vertical axis, which I'll denote by sigma. I'm going to use rho for the reflection, for the rotation, and sigma for the reflection. And this is more complicated. Reflection is a product of transpositions, and it's a little different depending on the parity of n. So when n is even, sigma looks like this. 2n, that's the transposition. 3n minus 1, it would be 4n minus 2, and so on, up to this. And n has to be even, otherwise n over 2 is not an integer. For n odd, it's 2n, 3n minus 1, but the rightmost transposition looks like this. So the pattern is similar, but these two are different. And I'm going to let you verify these equations. Now, it's customary, as I guess I've already said, to label the vertices of a regular polygon with the natural numbers 1 through n. But what we're about to do would actually be simpler if instead we labeled the vertices 0 through n minus 1, because we're going to use modular arithmetic, mod n. And so it's easier to control things. You don't have to keep saying, well, replace 0 by n, basically, if we relabel the vertices 0 through n minus 1. Okay. And so let's at least temporarily assume that we're going to label using 0 through n minus 1. Later on, we'll go back to what's more customary. Okay. Also, just for convenience, for a given fixed value of n, which we will have for the rest of this discussion, fixed n, we'll denote the residue class, the residue of an integer k mod n, by k bar. It'll make the arithmetic look a lot more readable. Okay, so if n is 5, for example, 7 bar is really 2. If n is 6, then 7 bar is 1. So with this zero-based numbering, what we can say is that two vertices are adjacent to vertex k. Every vertex is adjacent to two other vertices, one clockwise, one counterclockwise. The vertices that are adjacent to k are k minus 1 bar and k plus 1 bar. Okay. And that holds even when k is 0. So if k is that topmost vertex, then if you compute, so that's vertex 0, if you compute 0 minus 1 bar, this is negative 1 mod n, which is n minus 1. So that is the previous vertex. So if this was vertex 0, n is 0, this would be n minus 1. Okay. And when k is n minus 1, so it's the largest number, largest label, then the next vertex clockwise would be n bar, n minus 1 plus 1 bar, and that's 0. That's the top vertex. So if you draw a couple of pictures and label 0 through n minus 1, you'll see what's going on here. And that's why it's simpler to adopt this labeling set, because it's easy to describe for any vertex k the two vertices that are adjacent to k. Okay, now suppose that tau is a symmetry of the vertex set V, and that tau of 0 is k. Since the symmetries preserve adjacency, and the reason they do is because they preserve distance. Okay. And so they have to preserve adjacency. If two vertices are next to each other, they're a given distance apart, you could compute based on n, then those two vertices have to go to two other vertices that are adjacent, or the distance won't be preserved. And so tau has to send the vertex 1, we're assuming tau sends 0 to k, it has to send the vertex 1 to one of the vertices adjacent to k, because 1 is adjacent to 0. So it's got to send 1 to either k minus 1 bar or k plus 1 bar. And in either case, tau is completely determined by where it sends 1. If tau sends 1 to k minus 1 bar, so then we would have tau sends 0 to k, 1 goes to k, let's see, did I do that right? In the former case, so I've got these backwards. Okay. So I need to interchange these two. So let's look down here. In the former case, where we go to k minus 1 bar, 0 goes to k, 1 goes to k minus 1 bar, 2 has no choice but to go to k minus 2 bar. It can't go to, so this is the counterclockwise adjacent vertex. The clockwise adjacent vertex is k, but k is already taken in the codomain. So 2 has to go to k minus 2 bar, and so on. In the latter case, where 1 goes to k plus 1 bar, 2 has to go to k plus 2 bar. It can't go to k plus 1 minus 1 bar, because that's k, and 0 is going to k. Remember, these are bijections. So if you know where k goes, if you know where 0 goes, and you know where 1 goes, there are two choices for where 1 goes. That's it. The rest is determined. There are n possibilities for where 0 goes, because there are n vertices, and 2 possibilities for where 1 is sent for each of these n possibilities for 0. We now know that the symmetry group Gn of the polygon, or of the vertex set, has 2n distinct elements. So the order of the group Gn is 2n. Now, if rho is that one-click clockwise rotation that sends k to k plus 1 bar, then Gn contains the n rotations, the identity, rho squared up to rho n minus 1. Rho to the n now is n clicks, it's the identity. So rho has order n in the group, in the symmetry group. If sigma's reflection across the vertical axis, then the symmetry group of the polygon will also contain these symmetries. And it's not difficult to show. We already know these are all distinct because we can cancel the sigmas, and it's not too difficult to show that this set is distinct from this set. So we've got our 2n distinct elements. Okay. So Gn has this underlying set, which we'll write this way generally. Sigma to the I, rho to the j. I is either 0 or 1, so it ranges from 0 to 1, and j ranges from 0 to n minus 1. And we can also now find a commutativity rule by observing that if you start with 0, you apply sigma, so that's a reflection, and that does nothing. Then you apply rho, which will send you to 1, and then you reflect, you will end up at n minus 1. If you start with 1, you apply sigma. That will take you to n minus 1. You rotate, that will take you to 0 at the top. Then you apply sigma. That doesn't do anything. You're still at 0. So sigma, rho, sigma. Now, a sigma is an involution. It's equal to its own inverse. So this is really conjugation. Sigma, rho, sigma inverse. And that's an isometry, and we've just determine what it does to the 2.0 and 1, which means it's completely determined. Okay. And what does it do? It sends 0 to n minus 1 and 1 to 0. That is a one-click counterclockwise rotation. In other words, it's row inverse. So sigma rho sigma is equal to row inverse, which is the same as rho to the n minus 1. You can go one click counterclockwise. You'll get to the same place as if you go n minus 1 clicks clockwise. Okay. So we have this relationship. And that, by pushing the sigma to the other side, will give us two commutativity relations. Rho sigma is sigma rho inverse, which is the same as sigma rho to the n minus 1. Also, sigma rho is rho inverse sigma, or rho to the n minus 1 sigma. So these two equations say, in words, that we can slip rho past sigma in either direction if we change rho to rho inverse, or to rho to the n minus 1. And here are some figures to help you sort out that little bit of rotation and reflection stuff. So Gn, this symmetry group of the polygon with n vertices, is the unique group that fits the standard template Tn2 n minus 1, generated by rho and sigma, two elements. The order of the group is 2n, the order of rho is n, the order of sigma is 2. Commutativity rule: sigma rho equals rho to the n minus 1 sigma, or equivalently, rho sigma equals sigma rho n minus 1. Okay. So we have a complete description of the group Gn of symmetries of a regular n-gon for n bigger than or equal to 3. And this group, as I'm sure you've already guessed, these groups, I should say, for n bigger than or equal to 3 are the dihedral groups. Okay, so we now understand what the groups look like. This description has nothing whatever to do with polygons or vertices or labelings. This is simply group generated by two elements with these properties. So from now on, if we want to refer to the geometry of a dihedral group, we want to refer to the regular n-gon, we'll restore the customary labeling of the vertices from 1 to n. Here is the formal definition. For n bigger than or equal to 3, the dihedral group D2n is the group of symmetries of a regular n-gon. And it's defined abstractly by this standard template. And just to be clear, for reasons I'll discuss in a few minutes, the order of D2n is 2n. The subscript here in the notation denotes the order of the group. Well, I'll tell you now. Many authors will denote this group by dn rather than d2n. And I'll clarify that in a couple minutes. Now, I checked my library, and there are many books that I have that require n to be bigger than or equal to 3, and they're finished. That's the dihedral group D2n, or in other notation dn, n has to be bigger than or equal to 3. But there are some sources that like to define D4. That would be 2 times 2, so n would be 2 as the Klein 4 group. Geometrically speaking, we're talking about a 2-gon, which is going to be a straight line segment. Vertex 1 at the upper y-axis, vertex 2 at the lower y-axis, and you can still rotate. It's a 180-degree rotation, but reflection becomes trivial. So it doesn't really fit the template because, did I say reflection? I hope so. Reflection is trivial when you have a straight line segment on the y-axis, when you reflect along the y-axis. So this is violated. Reflection does not have order 2. So it doesn't fit this template. And the dihedral group D2 is defined to be the cyclic group C2. I wouldn't make too much out of this. In fact, maybe I shouldn't have even mentioned these two, but you may encounter them in some books that you read, so I felt like I should at least make you aware of that. Okay. There are other templates that will describe the dihedral groups, and therefore they are dihedral templates. Okay. This is the one we've already discussed. Okay. 2 generators, order 2n, rotation has order n, reflection has order 2, commutativity rule. And that commutativity rule has 4 different equivalent versions. It gets to be a little bit of a mess, but that's just the way it is, partly because sigma is an involution. So sigma is equal to its own inverse. And because rho has order n, and rho inverse keeps popping up, so it could be replaced by rho to the n minus 1. Okay. The thing to remember, if you can, is that whenever rho crosses sigma in either direction, you replace rho by rho inverse, which is equal to rho to the n minus 1. Here's another template that defines the dihedral groups T2n, order 2n, order of x2, order of y2, order of xy equals n. So this doesn't have an explicit commutativity rule. You have to derive the commutativity rule. So in words, the dihedral group D2n is the unique group of order 2n that's generated by a pair of involutions whose product has order n. That's quite a nice description. Okay. It's generated by 2 elements that are equal to their own inverses, 2 non-trivial elements, non-identity elements, but the product has order n. And here's a third template that uniquely determines the dihedral group, and that is a group generated by 2 elements, w and z, of order 2n, group is order 2n, and w squared equals z squared equals wz squared equals 1. As to part 2, its proof, we need to show these 2 templates are equivalent. This is the standard template, this is template T2n. So let's suppose first that a group satisfies the standard template. And we set x equal to sigma and y equal to the product, sigma rho. Then rho is equal to sigma y, And so you just multiply both sides of this by sigma. You'll have sigma squared, which is the identity, so rho is sigma y. And so x, y also generate the group G. You can go back and forth. Sigma is a word in x and y, so is rho. X is a word in sigma rho, so is y. These generate the same group. The order of x being sigma, of course, is just 2. And as to y, if we square it, we get sigma rho, push this rho across sigma to push it to the right, turns into rho inverse, get sigma squared, rho inverse rho, that's 1. And since y is not the identity, sigma rho is not the identity, y has order 2. And finally, xy, look at the template again. So far we've got our generators, and we've got the correct orders for the generators. We have to look at xy. Xy is sigma rho, sigma rho, which is rho. And so the order of xy is n. So G fits this template. So the unique group that satisfies this template, the standard template, also fits this template. But at the moment, perhaps there are other templates, there are other groups that fit this template. We don't know that at this moment. So if G does fit this second template, then now we can turn the tables. We can let sigma equal x and rho equal xy. Then y is sigma rho, and so again the two sets of elements generate the same group. Order of sigma is 2 because sigma equals x. Order of rho equals order of xy, which is n, so the orders of rho and sigma are what they should be, order n, order 2, and rho sigma is xyx, which is x, y inverse, x inverse, because x and y have order 2, they're equal to their own inverse, and that's x quantity xy inverse, which is sigma rho inverse. So G satisfies the standard template. So these two templates, the standard template and this template T2n, are satisfied by precisely the same groups, and therefore they are equivalent, and so T2n is also a dihedral template. And I'm going to leave part 3, for you to prove. Okay. But if you study the example we just did, you can see how you the general approach to showing the two templates are equivalent. Excuse me. Especially when you don't know that both of the templates are satisfied by a unique group, then you have to go both directions. Okay. If you knew that both templates are satisfied by a unique group, then all you have to do is show that if a group satisfies one of the templates that satisfies the other, then you know they're equivalent. But we didn't quite have that situation here because we don't know about uniqueness for this template. Let me now clear up the business about the notation. We denoted the dihedral group of order 2n by d sub 2n, as many authors do, but many other authors denote the dihedral group of order 2n by d sub n. And that then index reflects the number of vertices in the polygon rather than the order of the group. And there's nothing wrong with that, except that now there's ambiguity, so every time you look in a book and you see a symbol for the dihedral group, you're going to have to sort out what the author means by that symbol. There is actually precedent for both styles, you might say. C sub n denotes the cyclic group of order n, but S sub n denotes the symmetric group on n symbols. The problem with the dihedral group is that the two different notations are used for the same group, so it can be confusing. Let's take a look now at the center of the dihedral group D2n. The dihedral groups D2 and D4, when they're defined, are defined as abelian groups, so we don't need to worry about them. So we can assume that n is bigger than 2. Now, if A is an element of D2n, then it will be in the center of the group if and only if it commutes with both generators, rho and sigma. So if k lies between 1 and n minus 1, then let's look at this element, sigma rho to the k. It will commute with rho if and only if sigma rho to the k plus 1, which is sigma rho to the k rho, equals rho sigma rho to the k, which is sigma rho to the k minus 1. Because when we move this rho across this sigma, it becomes rho inverse. So sigma rho to the k will commute with rho if and only if, when you cancel here, rho squared equals 1. But that's false. As long as n is at least 1, then, oh, actually, we've already dispatched those two cases, so say for rho bigger than or equal to 3. Okay. So none of these elements, sigma rho to the k, for rho for k in this range, lie in the center, because they don't commute with rho. So the only possibility for elements in the center now reduces to just the powers of rho itself. No sigma rho to the k's will work. Okay. We know, by the way, sigma doesn't commute with rho, so that's also not in the center. So these are the only candidates left, the powers of rho. Now, rho to the k commutes with sigma if and only if sigma rho to the k is rho to the k sigma, which is sigma rho to the k minus, to the negative k. Because as you move the sigma across, or you move the rho across to the right, each one becomes rho inverse, so you get rho to the negative k. And that's equivalent to rho to the 2k equals 1. And that occurs if and only if n divides 2k, because this is telling us that 2k is an exponent of rho, so the order has to divide the exponent. So in other words, 2k has to be, say, m times n for some positive integer m. The problem here, though, is k lies in this range. So m has to be 1. Otherwise, 2k will not fall in this range. 2k will be at least 2n, so k won't fall in this range. M has to be 1. 2k has to be n. So if n is odd, no such thing. Center is trivial. If n is even, the center contains these two elements. The identity, iota, and rho to the n over 2. You can see this from a geometric perspective. This equation here is equivalent to rho to the k equals rho to the negative k. So a k-click clockwise rotation has to be equal to a k-click counterclockwise rotation. You have to get to the same location by going k times clockwise or k times counterclockwise. How many, for which polygons does that work out? They have to have an even number of vertices. And you go halfway around clockwise or halfway around counterclockwise, you come to the same place. And the target of either one of these rotations is the vertex directly opposite the vertex 1. So it's the vertex on the negative y-axis. So here's a summary. These are the centers for D2 and D4, and then the center of D2n is either trivial when n is odd or equal to, I don't know why I didn't put iotas there, for n even. Okay, so the analysis here, determining the center, was just a matter, since the group is finitely generated by two elements in particular, was just a matter of figuring out which elements of the group commute with both the generators. And so it's just a little algebra, basically. It can get a lot more difficult to compute the center of a group, but in this case it wasn't really terribly bad.